Lists can hold anything, numbers, strings, even other lists. So why does Python need a whole separate type just for looking things up? Here's the catch. The moment you use lists to tie one piece of data to another, a name to a grade, you quietly sign up for a fragile bookkeeping contract. Today we'll feel exactly where that contract breaks and watch it point straight at a better structure, the dictionary. A dictionary is a new compound type, like lists and tuples, but it behaves very differently, and the fastest way to see why is to hit the wall without it first. Suppose we want to store grades for a class. With only lists in our toolbox, a list is a sensible pick because the data keeps changing. Students join, students drop, grades get updated, so we want something mutable. Start simple. For each student, we'll keep just two things, their name and their final letter grade. One natural approach is two parallel lists. One holds every name in the class, the other holds every grade. Then we impose a rule on ourselves. A given position means the same student in both lists. Position 0 is Anna, and over in the grade list, position 0 is her B. Position 1 is John, whose grade is A. Position 2 is Denise with an A, and position 3 is Katie with a B. Notice that nothing in the code enforces this. The alignment is an unwritten promise we have to keep by hand. Now let's look up one student's grade. We write a function, getGradeList. It takes the student's name, the list of names, and the list of grades, and it leans entirely on that parallel index rule. First, he asks the names list for the position of the student, pass in Anna, and the index method hands back 0 because that's where Anna sits. We save that position in the variable I. Then we read the grade list at position I, which gives back the matching grade. Finally, we return the student paired with their grade as a tuple. Call it for Anna, and out comes the pair Anna and B. This works, but it gets messy fast. If the class is large, picture every student at the university, we're passing giant lists around as parameters. Add micro-quiz scores and problem set scores, and suddenly there are even more parallel lists, and every function that looks something up must accept all of them. Mutation is worse. When a new student enrolls, you have to remember to append to every single list. When a student drops, you have to delete the same position from every list. Keeping several lists perfectly in step by hand is a fragile design. One slip and they fall out of sync. Let's attack that sync problem. Instead of many separate lists, put everything inside one master list. It has one element per student, a sublist for Eric, one for Anna, one for John. Each student's sublist holds 3 parts, the name, then a labeled list of problem set scores, then a labeled list of micro-quiz scores. Those labels are just strings sitting as the first element of each inner list, PS for problem set, MQ for micro-quiz, telling you what the numbers after them mean. Now there's only one structure to maintain instead of a growing pile of parallel lists, and adding a student means adding a single sublist. Getting data back out now takes a nested search. The function getGrades takes who we want, what we want, problem sets or micro quizzes, and the master list. The outer loop works student by student, comparing the first element of each sublist against the name we asked for. Once it finds the right student, the inner loop drops one level down, scanning that student's labeled lists and checking each label against what we asked for. On a match, it returns the student's name together with that labeled list. Ask for Eric's micro quizzes and you get back Eric paired with the micro quiz list 6 and 7. Ask for Anna's problem sets and you get Anna with 10, 10, 10. It works, but read that function again. Nested loops, nested indexing, and a data layout you have to document carefully before anyone else could safely touch it. Don't worry about absorbing it in detail. We're not keeping this approach for long, and you're still not finished. What comes back is a tuple holding the name and a labeled list, so reaching one single quiz score takes 3 more subscripts into that result. We remove the sync problem and pay for it with code that is genuinely hard to read. Step back, and both attempts were secretly doing the same thing. In the parallel list, a name was a key that pointed to a grade. In the master list, the labels problem set and the micro quiz were keys pointing to their scores. Every version of this problem is really about associating data with a key. That is the whole idea, and the dictionary gives it to you directly. You hand it a key and it hands you the value. No index bookkeeping, no nested search. That is the structure we build next. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.